time to join this talk. I hope that I can answer some of your questions. It's more of an interactions. It's not just I'm giving a talk and then you're listening. I'm expecting a very interactive session here. And since the audience is not that too large, it can be easily very informal kind of a discussion here. Okay. But I'll be kind of conscious in the interest of time because we almost like 12 minutes past the time. So I expected the talk and the question answer will be an hour, but now it is kind of truncated. But that's okay. Depends on the interest. I can accelerate and also I can zoom in more time on some particular slides. But as Duran said that the talk that I wanted to give here is on differentiated fully depleted SOI technology. As someone already pointed out that some of you are familiar with this technology. But the whole purpose here is to talk about how differentiated silicon technology can address the need of millimeter wave applications. And that includes not just 5G or future 6G, it can be other applications like satellite communications, for example, right? And even sensing. I'm not going to all the details today, but that's the purpose of this talk because a lot of people when I talk to, and again, I'm not saying they're old school or anything, but they believe that millimeter wave and higher frequencies belong to compound semiconductor materials, right? And they're not wrong, to be frank with you, because that's the way compound semiconductor always goes ahead of silicon for higher speed, higher frequencies, right? So there is nothing wrong about that. But what we can show here that if you have a differentiated silicon technology tailor-made for these applications, you can still do those things, and that probably a better sense of doing it for a product level than doing just 2.6 or 3.5 materials along with silicon for computing, right? And that's the purpose of my talk here. Please feel free to stop me at any point. Before I proceed, I want to ask you, can you guys see my screen okay?
Yeah.
Okay. I will just go flip one slide at a time, but in any point, if you want to stop me, please chime in and we can talk, okay? So I will start with this slide to set the tone for the rest of the presentation, which is we call it industry mega trends, and that's enabled by technology, right? Now, what we mean by mega trends, if you think about most of the applications that you are doing today, not all, but most of them, I'm talking about in the electronics, whether it's say industrial, compute, consumer, or even medical applications, it has three components, right? If you think about it, it's connecting, sensing, and computing. Now, of course, there are so many other things there, but I'm just talking about where the future basically goes to a new kind of evolution, right? So these are the places. Of course, there is a power management, how to save batteries. There is a whole new areas are there. But if you think about the broad perspective of these applications, it's basically connecting, sensing, and computing, right? So we call it, in terms of future evolution for these three categories, we put it under frictionless networking, and I will explain to you what I mean by that. And then there's a virtualization. Virtualization is a big term. It's not just for sensing only, but of course, sensing is also merged into virtualization in the concept. And last but not the least, hierarchical artificial intelligence. That goes to the computation domain, right? The whole computation paradigm is being shifted, and it will be, as we go forward, and artificial intelligence, the way we'll use this term will be much more pervasive than it is today, right? So let's start with frictionless networking. And most of my talks will be on wireless part of it, which is millimeter wave. So I'll spend more time on this part rather than the other two. So as we see that there is a huge demand for data, right? And that's increasing. According to Cisco, today it is around 20 zettabyte, and it can go to almost 10x by next 5 years, right? And if you go further, it will be exponentially increasing further. So there is a huge demand on data. It's two things: is the volume of data or the data traffic, and also the data rate, right? And both is a challenge right now, right? And that's the way we evolved from 2G, 3G, 4G to 5G, right? Now, if you look into the future, a lot of applications that will be kind of driven by these virtualizations to a great extent, and other applications also that will demand data rate almost like 100x in the next decade, right? If I put 1 gigabit per second as a baseline, it's not necessarily all of us is getting the privilege of having that, but if you take that as a baseline, 100x, like 100 gigabit per second by 2030, right? So that's where we are driving today from the mega trends. Now, it's very important to understand the enabled by technology term here, and that will be some of the discussion that we have in next of the few slides. Okay. Let's talk about how technology drives this kind of applications and where 5G comes in. Now, I'm not going through all the details of these inner and outer circles, but the point is all this future application that I'm mentioning here is ultimately a fusion of 5G from the wireless connectivity, AI, the computation part of it, artificial intelligence, and IoT. The IoT is coming in because the applications are not just cell phone based, right? It's not just mobility based. There are a lot of machines interacting with each other without even human interference, and they can interact with the human, they can interact with each other, and that's where IoT comes in. So the combination of 5G, AI, and IoT leads to plethora of applications here as we go forward, right? And we call it a interaction between future of human and machine communications, and that's where 5G is all about. So what 5G has to do in order to deliver what is expected out of it? There are four main things basically, and that's, I'm putting this slide as a kind of a segue to my technology discussions, right? So for 5G implementations, it's extremely important to understand and recognize that there's a complexity in terms of implementation in devices, and cost is a very important factor there, right? If you want, you can put a lot of functionality into your handset. Not only it will be bigger, but it will be cost prohibitive, right? And do you really need that? So the question would be, definitely it's a question of integration and scaling within the fixed form factor. You guys are hearing about this flip phone, folded phones, and in fact those things are coming back, right? We are used to those things in 2G 3G days, but it's coming back again. And basically the whole idea is to how to give more real estate, and I call it the probably one of the most expensive real estate in the world, right? How much real estate you want in a handset. But that's coming, but at the same time huge complexity. There is an interaction between legacy standards like 3G, 4G with 5G. That's one. And number two is how to make it power efficient, how to make it more efficient from the antenna perspective. And these are all difficult things to do because the form factor is a question. So that is the device complexity and cost questions. The number two is power consumption. So I refer to battery. You can have two batteries just buying a folded phone, but that doesn't solve the problem. The problem is, as you go forward to higher data rate, more functionality in a phone, we didn't use the phone in 2G, 3G, even 4G times with the functionality we are doing today, right? So what it means, everything you use, it basically causes the battery power to be bled. And how you have to make sure the application that you are running is efficient is not just making a kind of a huge battery or making the battery kind of sufficient for your purpose. How the technology can drive those applications to reduce, or basically the power consumption is reduced there, right? That's one thing. The third thing is network densifications. I will talk about today the phased array part of it. And that's where it's important. And we are seeing that even in sub 6 gigahertz today, right? Massive MIMO that's happening in sub 6 gigahertz 5G and in 4G as well. It calls for more densification, right? So we are talking about more small cells rather than macro cells here. The coverage, there is a huge traffic, data traffic or density of the traffic need. So we are addressing it by more small cells rather than in one macro cell covering 30 kilometers of coverage, right? So that's another important point, because what it means is not just the question of utility bill and how carriers will support it. The question is how to make an efficient cell tower communicating with your device, right? That's basically what network densification is. It's an investment on one side and also efficient investment on the other side. It's very important to understand. And last but not the least, the security and reliability. I am not going to the security, it's a topic by itself, but reliability definitely I'll address today because that's where technology comes into picture. Now, you can replace your phone if you have money anytime in a day, but the carriers don't have the option of replacing a tower whenever they want to, right? That's where reliability comes into picture. So we have to make sure we have a reliability inbuilt while developing the technology for the hardware, so that you don't have the problem of churn, right? You have an outage just because the device is not working in the cell tower. And that's the reason reliability is extremely important, more so when the densification is huge. I'm not spending too much time on this. You guys are all familiar with the three facets of or usage scenarios of 5G. I will mostly focus on the enhanced mobile broadband applications today. There is a whole new game of massive machine type applications like IoT, and also there is an ultra reliable low latency application, which is like this V2V or V2X communications that we have already started, but it will be much more so in the next decade, right? But I'll be mostly concerned with this enhanced mobile broadband applications, which one of the very key usage scenarios of 5G. Okay, please stop me if you have any questions. I'm going to the general kind of overview before deep diving into the technology. So let me go to the next slide. Oops, I clicked it too often. Maybe a couple of more. Okay, so let's talk about, in order for a technology, in fact, I probably skipped one slide. I just want to stop here, or maybe here. So other than 5G, there are applications like satellite communications. I'm sure you guys are hearing that there is a broadband internet to be serviced by low Earth orbit satellites. And that's also fall into microwave and millimeter wave range. Some people are thinking about even E-band in future, right? So again, I just wanted to mention here because that's also based on phased arrays, whether it's in the satellite payload or in the ground terminals. But this is also falls into the same category that I will talk about from technology perspective. Now, before going further, I want to introduce the concept of phase array antenna system. Some of you already know about it. There are three different classes of it: analog beamforming, digital beamforming, and hybrid beamforming. And what analog beamforming is, we do the beamforming, which is basically the constructive interference and destructive interference where you don't need the energy to be focused in the RF or millimeter wave domain itself. You can do in millimeter wave, you can do in IF, or you can basically that's where the analog beamforming comes in. Whereas digital beamforming, you basically do the beamforming in the digital domain. So you convert it to baseband after ADC, DSC, and you do the phase shifting, combining everything in the digital domain. That is digital beamforming. And last but not the least, there is called hybrid beamforming, which is basically a combination of both. So, from analog beamforming perspective, it's a very cheap solution compared to this other two, particularly with respect to digital beamforming, but it's very difficult to implement when the number of antennas become huge. Because when you combine more than 4 antennas at a time, giving and allowing for the phase mismatch errors is really become very tricky, right? So it works for a handset perspective, and I'll talk about that next, that if the number of antenna sets is 4 or even 8, for example. I haven't seen any analog beamforming beyond 8 to date, right? So that's where it works very well, but it's very tricky. So that's the reason it's kind of okay for a small number of arrays. On the other hand, digital beamforming, it's a very elegant solution. It's like extending the idea of non-beamforming solutions to beamforming by doing a kind of a multiplicity here, right? So you can think about each of the path I'm talking about. It starts from one antenna element. So this is no different from what we do in our sub-6 gigahertz today, right? So each antenna element is a switch, receiver, transmitter, up-down converter, ADC, DAC, go to the modem, right? So from up to that point, it's kind of similar. Only thing is that there's a multiplicity because of the fact there's a number of antennas for beamforming. So we basically delay the decision of beamforming at the digital domain after converting to baseband. The downside of this is that it needs more bombs. The number of elements or components is much more. And also at the same time, the power dissipations is huge. We have only one ADC DAC here. It can be coupled, depends on if there is a different way of implementing. But here it scales with the number of antennas. So ADC DAC burns a lot of power. And same thing is true for up-down converter, because now you are having one up-down converter for each element, right? So this is also not a good solution to go to a huge number of elements, but some people are still trying that because this is a very flexible and modular way of doing things, right? Let's say you want to go from 4 to 8 to 32, you just repeat those things, right? It doesn't change your whole the design process. So this is a very flexible way, but the downside is the cost and also the power dissipation. Hybrid beamforming combines the virtues of both. It's starting with the analog beamforming and then do some of the decision making on beamforming and adaptability in the digital, right? And most of the infrastructure based approach is based on hybrid beamforming because the number of antennas are huge. Okay. Please let me know if you have any question, because otherwise I will basically go very fast before going to the technology side.
Yeah, sorry, I have a quick question. What does FEM stand for in this
FEM
context?
is the front-end module. Sorry about not explaining that before.
Yeah, no problem. Thanks.
So this is the three blocks, right? This is the one is the front-end module. A lot of people call the front-end module stops here, but there are other people that say that, okay, front-end module consists of the millimeter wave up-down converter as well. So depends on who you work with. And high IF transceiver is because when you deal with millimeter wave, even 24 to 28 gigahertz, your IF is not like a zero IF that you are used to in your cell phone, right? It's not like 0 to 40 megahertz. It's much, much bigger than that. We call it around 8 to 12 gigahertz because you want to make sure IF doesn't cause any interference with your sub 6 gigahertz electronics, right? So basically just crossing that 7 gigahertz, so 8 to 12 gigahertz. That is the high IF transceiver part of it. And then integration with 22 FDX is basically what we are saying is, if in some holy grail you can integrate the whole thing, and that's only possible in a digital beamforming, because here it doesn't make sense. I'll explain to you why.
Mm-hmm. Okay.
Any other question? No? Okay. So here I'm showing a kind of a classic example. And again, millimeter wave handset is already out. It's kind of the first millimeter wave handset came out in 2019. So we are looking at 19, 20, 21, basically Samsung S21 is released, right? So even though it is only confined to North America at this point, because other countries don't have the infrastructure, Korea is very close and they will be probably having some next half of this year. Japan probably go next. But other than that, there is no plan in China or Europe at this point, the other two big markets. They will do, but not at this point, right? But having said that, what is already implemented in product is the following. So we place the antennas in different parts of the handset. Some people do 3 antenna modules, some people do 4 antenna modules. iPhone 12, they do 2 antenna modules, right? The whole purpose here is to have some kind of diversity. So when you hold your phone, if you block one of the antenna module, millimeter wave attenuation is huge. So you want to make sure that at least one antenna module can see the tower or the whatever the nearest access point clear, right, in line of sight. So that's the reason there is a redundancy here. The point here is the front end module that you asked me the question. This is where the antenna module rests. You can ideally you have to basically convert the signal to IF, because otherwise this interconnect length is too long for a millimeter wave attenuation, right? Millimeter wave attenuation is huge. It's like pretty much like 1 dB per millimeter, sorry, 1 dB per centimeter. And that's also based on the best board that you can get, right? Actually, it's even higher. So you don't want to have a long interconnections on millimeter wave going to the next chip, right? So you wanted to convert it to a lower frequencies, like as I said, that 8 to 12 gigahertz IF. And that's the way it is implemented today. And then of course there is a transceiver and going to the mod. So that is the way it is implemented today. Okay. Now I will go to the guts of these things. What are the technologies that it consists of and what are the challenges, particularly for differentiated FDSOI. So before going to technology, what are the essential elements that basically a technology should have for millimeter wave, right? And I'm talking about silicon technology here. The first thing is, of course, the technology is capable of addressing the high performance need for millimeter wave. What it means in terms of basic technology term, the FT max should be at least 3x, preferably more than 5x of the application frequency. So let's say there is a 30 gigahertz carrier frequency. We are expecting the FT max should be at least 3 times, but that doesn't happen because when it is 90 gigahertz, the flexibility the designer has is very, very little, particularly because of the fact the linearity that you have to have in your transmitter, you have to have a lot of back off, right? So then the basically efficiency goes down, and that's the reason you want to make sure the FTF max is at least 5x. That means we are talking about at least 150 gigahertz. There also we find it out that it's not good enough because that doesn't give too much margin to the designers. So we go to even 10x. Now that 10x is not sustainable if the frequency goes up. For example, if we go to 60 gigahertz, we don't have any technology at 600 gigahertz fmax today, right? There are a lot of papers published out there, but there is no that something commercially available. So at that point, you have to start reducing the x lower, right? So 5x is possible there. When you go to more than 100 gigahertz, ultimately we'll settle to 3x kind of numbers here. But the point is, your technology has to be capable of addressing the performance need. FTF max is one of them, but there are other figure of merits as well, like self gain. gain efficiency, right? For the receiver, very important, the NF mean of the transistors, and also the phase noise, right? This is basically 1/f noise is the very critical element to determine your phase noise. So your technology has to have very low 1/f noise, very good NF mean for your transistors, and at the same time, the amplifier should have a very good self gain and gain efficiency. So that's from the performance perspective. Very important to understand the back end, right? Because we normally take back end for granted as long as you have a very good transistor on the front end. But that's not true for millimeter wave, because there is a huge attenuation on the interconnections, right? And also on the passives. So the way to address that is thick top metal. So you have to basically develop a technology for millimeter wave with a thick back end. And at the same time, the distance from the substrate has to be larger, because substrate by silicon, by definition, is lossy, right? Unless you do some kind of a substrate resistivity kind of things that in your handling a substrate. And we'll talk about that, right? So there are ways of addressing that, but it's very important. Last but not the least, here is the two other things is well-modeled technology. So that's where PDK comes into picture, right? So PDK for sub-6 gigahertz is one thing. There's a totally different ball game to have applicability of your models to a higher frequency like 37, 39 gigahertz. And at the same time, it's a kind of very good model hardware correlation. Reliability, I talked about briefly, but it's extremely important that the reliability that we take it for granted for a kind of a technology that has been around. Like, for example, just take an example of 28 nanometer. It has been around for quite some time, right? For different applications. And reliability is taken for granted. But now, when you apply the technology for a millimeter wave, you have to really find it out what is the safe operative area for that technology for millimeter, right? It's a totally different ball game here. So both reliability and ruggedness perspective from millimeter wave, right? So it's extremely important for the foundry to assess those things before making it available for commercial purpose. So this is the fundamentals. Now I am going to the technology details, right? So the three technology that I will refer to today, I'll mostly talk about 22FDX, but I will also refer to the two other technologies. So what basically decide which technology we'll use for millimeter wave? The three different the parameters are performance, integration, and reliability. Now, I put performance and power together here because you cannot have a performance bleeding too much power from battery, right? You have to have an efficient transmission at the same time. So performance, power together, integration, and reliability. Now, if you really need raw performance, which is basically for an infrastructure perspective, for example, SiGe is the best technology. It can generate efficient power compared to any other CMOS-based technology, which is RFSOI, the PDSOI, or FDSOI. It is also a reliable technology, at least from IBM or now a Global Foundry's perspective. We have basically worked with silicon germanium for almost like 3 decades, probably even more longer, right? So we know how to handle SiGe, and SiGe has been addressing millimeter wave for defense application, A&D applications for quite a long time, right? So this reliability has been evaluated for a long time. So it's a reliable technology. It can address the best performance that's possible in a silicon technology. Integration wise, this is not the technology you want to go to, right? And that's where the next two comes into picture. So you have this partially depleted technology, which is 45 nanometer. It can address performance, reliability, and integration both. And integration is from the front-end perspective, not from the transceiver or from the modem perspective, right? So, for example, if somebody wants to do a digital beamforming, not necessarily he will go to 45 RFSOI technology for that purpose, right? Because he probably wants to integrate some of the digital phase shifting also into this technology. That's not the technology for this. But if you want to integrate the whole front-end module that I showed, this is probably the best optimum technology at this point, right? Both from performance, power, reliability, and integration point. Last but not the least, 22FDX. Now, the fact that it's 22 nanometer, of course, it can have more digital density from memory on logic perspective, right? So it can do much more integration. Is it as high performing as SiGe and 45 SOI? Probably not. Is it as reliable as these two? Yes. And what about integration? Much better than compared to two. So basically, we talk to our clients based on their needs, either of these three technologies, right? And these are all silicon-based technology. We are not talking about gas or GaN kind of technology or indium phosphide here. It's all silicon technology, but these are all differentiated technology. And that I'll explain to you in next few slides, what I mean by that, okay? So let's start with SiGe. So SIGI, you can have a BiCMOS technology. So where you have a silicon germanium heterojunction bipolar transistors with CMOS, which basically takes care of a lot of controllings, gates, and other logic and memory part of it, right? It's a BiCMOS platform from that point of view. Now, if you don't want to do CMOS, if only the SIGI part of it, there are some standalone SIGI applications as well, which is basically driven by SIGI HBT, right? But I'm talking about BiCMOS here. Now, there are a lot of way of engineering that, but the point here is this is the technology optimized for RF millimeter wave applications. And why it is so? Because you don't have to go to a lower node to have a better performance of HBT, right? It's a vertically defined technology. What you have to do, basically, you have to make the base thinner and thinner for your transit time to be improved. But you can gain something with a better litho from the parasitics perspective, but it's mostly defined on a legacy nodes. Like, for example, 130 nanometer is very, very attractive today from infrastructure perspective in millimeter. If you go to a lot of millimeter wave base stations today for fixed wireless or mobility, you still see silicon germanium from 130 nanometer, right? You don't need to go to lower nodes for that purpose. But what advantages you can bring to lower nodes is two things. One is you can make higher density of logic along with the raw performance of silicon germanium HBT. And number two is you can also get some advantage of advanced litho when you go to lower nodes, right? And that addresses some of the parasitics in the HBT construct, right? So today we have more than 300 gigahertz Fmax in production today. And there are some publications to show that silicon germanium technology can go even 700 gigahertz for Fmax. It's a publication, not a production level. But we believe that this technology definitely can go beyond 300 gigahertz. Some people think it can go to even 1 terahertz Fmax, right? Again, depends on who you ask. But definitely from performance perspective, a low phase noise perspective, and higher breakdown voltage perspective, this is probably the best silicon technology. I talked about some of the things. This is all in public domain. So IBM Ericsson has a JDA, and they demonstrated that. I think it is 2017 Mobile World Congress. They demonstrated that. It's all public knowledge, and it's a lot of papers from IBM as well. I was part of IBM at that point. So they developed a 64 dual polarized antenna, and that has been used by Ericsson in different products already. So there is a product proof point. It's not in just some professor's research anymore, right? It's out of the lab, right? So it shows the very good performance of EIRP, very linear, right? You can see that even at the high, when you number of antenna elements increases, they can maintain that linearity in a log scale, of course, in EIRP. So almost like 60, almost close to 60 dBm kind of EIRP they can get there. And it can show the beam steering controlling part of it as well, right? So enough proof point to show that silicon germanium is already there, and it's at the product level. Let's shift gear to SOI, where basically most of my talks will be today. So SOI has the inherent advantage that you can do stacking. And because of that, it can kind of overcome the intrinsic silicon Johnson limit, right? If you basically show the performance of transmission power versus frequency, there is something called Johnson limit, and that's the intrinsic limit, right? So the fact that SOI can cross the Johnson limit because it goes beyond silicon to something called stacking, right? You can stack transistors, and that's a very efficient stacking. And by doing that stacking, which is not possible in a bulk semiconductor, you can do many things. You can basically have a higher power tolerant switches and power amplifiers. And at the same time, it also basically do reduce parasitics, right? Because the way you do that, you shut off by a shallow trench isolation up to the box. That is the construct of this. I'll show one example. And that way you can make sure that reduce parasitics, that can take the transistor to higher frequencies. You can have better noise figure, and also the passives, right? Because there is a box layer, it makes the Q of the inductors or MIM capacitors much better compared to bulk silicon, right? And also another important thing is it's scalable, unlike 3.5 materials, because 3.5 materials still in the 4 and 6 inch, right? Some people are going to 8 inch for GaN, but mostly 4 and 6 inch. Here we are talking about 12 inch material. So the better economics there, and also at the same time, very good performance if you can make that, right? And that's where the differentiated technology comes into picture. Let's start with 45 nanometer before I go to my topic of fully depleted transistors. So here in a partially depleted transistor in 45 nanometer, as I said, you can integrate switch, LNA, PA, and phase shifters. Very good FTF max. In fact, there are some construct that we have recently released externally that we have a PA which can go even 25% higher Vmax, and that gives you capability of better transistor output matching, right? Because it's extremely difficult when your output impedance is very low and you have to deliver to a 50 ohm load, right? So there is a lot of efficiency loss happens there. So we basically could address that. We can basically go to a higher voltage, which makes our output impedance better, and we can have a very efficient matching at the output, number one. Number two, it also improved our PSAT and also the efficiency. It's very important to understand that, right? So that's we have done that. And as I said, if we can go and have a higher resistivity substrate, your passive losses reduces, and it's very important from the matching perspective, from efficiency for transceiver, for example. And last but not the least, we also have to develop something called optimized backend for millimeter wave. What we did, the trick is thick metals, but very much away from the stack height. We are increasing the D, we are increasing from the lossy substrate as much as possible. By doing that, we have shown that with a high resistivity substrate, we can gain around 0.7 dB kind of a reduction in insertion loss when you measure those interconnections, right? And that's a huge from the millimeter wave perspective. And this measurement has been done in 28 gigahertz, but the conclusion is similar to higher frequency as well. So with those tricks, we can say that this FDSOI technology at 45 nanometer is kind of a unique offering from global foundries. It can address the whole integrated front-end module. We have demonstrated that in 24 to 28, 37 to 39, and even at higher than 50 gigahertz. But again, of course, there is a commercial product there from the access point perspective. From the backhaul, we have done from E-band, which is 71 to 86 gigahertz band, using this technology. Now, this is a chart. Many people questions me, but I wanted to still show it, our view. What I'm plotting here is the number of elements of antennas you need on this part of this y-axis, and the array power consumption on the other side. Now remember, this is array power consumption. I'm not talking about the power consumption from the transistors, right? And this is the average power output. So of course, if you go to higher output power, you have to go to 3.5 material. Gas probably come here, GaN, right? That's the way. Indium phosphide is also coming there. But the point here is, if you use bulk CMOS, you need to make the same EIRP limit of 65 dBm. This is an example. You can go to higher EIRP. You have to use more number of elements, right? That's where this point is. Huge number of elements you have to put. On the case of GaN, you don't need much number of elements. And that's the problem with GaN, right? Because if you can gain a 65 dBm with almost like a 1/6 or 1/8 number of elements, you are not taking advantage of the array gain. So you are basically burning power into the transistor itself or the PA itself, right? And that's not the good thing. And that's the disadvantage of using a GaN. It's good for the perspective of if you go to very high frequency where there is no offering from silicon, you have to have an efficient transmitter. GaN is the way to go. Indium phosphide, same way, right? But in the domain of Ka band, for example, 24 to 39 or even 47, you are basically not taking advantage of the array gain because the number of arrays are less. And at the same time, integration, right? If you have to integrate the whole FEM, GaN has no answer for that. And that's where RF-SOI coming in between is like optimum solutions. Not too many antenna elements like bulk CMOS, a very good usage of array power consumptions and integration, right? So that's the way I explain this curve. Please let me know if you have any questions. If there is no question, I'll go to the my main topic here, which is almost probably around 15 minutes. I'll cover that, which is basically 22 FDS technology. Now, 22 FDS technology is meant for millimeter wave SOC. It is not meant for millimeter wave, the best PA around or best LNA around. In fact, the LNA is very good, by the way, but still, it's for SOC. What we do is it's a very good FTF max technology with a very good high self gain in millimeter wave domain, and also for the receiver perspective, very good phase noise as well. But the trick we play is using the back bias, which is the body bias we can use because the box thickness is very thin, right? And that's the reason you can use a secondary gate here. Why we do that? We can do for many purposes. You can speed up the transistor, number one. You can reduce the leakage if you do reverse bias. And at the same time, you do post-processing. Let's say somehow your yield is not to meeting the target of the client. You can always tune this for your parts, of course, individually, for the lot by lot basis. And at the same time, you can meet the specs. So that's a huge advantage that extra knob provides that. And that is the 22FDX play here. Now, what this technology does, as I said, it's a SOC technology. This is not meant for raw performance of silicon germanium, but from compared to bulk CMOS, and we have taken bulk 22 CMOS technology as a reference here, 50% more performance, 70% of more efficiency in terms of DC power consumptions. And at the same time, it can integrate FEM, it can integrate transceiver as well, and digital front end. There is some use cases for that as well, right? So I will go to some details of each of them. So the way we talk about the normalized figure of merit is FT-GM over I or Fmax GM over I. It's not FT-Fmax or nor GM, right? Why? Because it's extremely important to understand FT-Fmax is good, but how much power you are burning in order to get that, right? And that's the reason this FT-GM over I or Fmax GM over I comes. Here I'm give an example of comparison between 22FDX, 14 nanometer FinFET and 20 nanometer FinFET. And this is all global Foundry technology, by the way. So we are not sharing anything which you are not supposed to. So here you can see that FT-GM over I, 22FDX is the best. The point here is actually from this point of view, we are basically biasing at almost similar kind of bias current from the microamps per micrometer perspective, but we are getting more FT-GM over I. In case of Fmax GM over I, we can definitely see that 22FDX is much better because 14 nanometer FinFET suffers from parasitics, right? So the Fmax is not that high. GM over I is extremely high, by the way, for FinFET, but not the product. And that you can see that. So here the peak is at a lower bias current, that's for sure. That is the advantage of FinFET. But then for the raw, the number of Fmax GM over I, 22FDX is better. Bulk is, of course, not as good as that from the point of view. So with that in background, I will show you some of the silicon proof point from the circuit components perspective. Let's start with PA. Now, PA is where basically the make and break of a technology for millimeter wave perspective. There are so many technologies good for receiver perspective, but not for transmission, right? So here we are showing some examples of 2-stack and 3-stack PA. This is a 2-stack PA, and we have achieved a PSAT of around 16 to 18 dBm, depends on what kind of topology it is. And also the peak PAE is the peak PA, is not that the PAE will operate, is around 30 to 40%, depends on the topology again. It's a very good number from millimeter wave perspective, but as you back off, of course, your PAE reduces, right? We know that. But just basically to show the strength of this technology, right? And we basically say this is the best RF SoC technology for millimeter wave perspective. LNAs, we have demonstrated LNAs in 28 gigahertz. Very good gain, more than 10 dBm, 10 dB kind of a gain, very good linearity as well. But the important things to understand is the noise figure. We have some results which is going to even 1.3 dB, but this results is at 24 gigahertz. It's kind of dated like 2019. I'm showing it here because it's already explained externally. And important thing is the DC power, which is basically around less than milliwatt, 10 milliwatt, right? So you are dissipating less than 10 milliwatt. You are achieving a noise figure of around less than 1.5 dB and very good gain and linearity. And that's what this technology platform offers. Switch is also a very good from performance perspective, very good insertion loss, very good linearity from the intermodulation perspective. And even at 80 gigahertz, you have seen that the insertion loss versus frequency curve, it doesn't go too bad, right? 1.7 dB insertion loss at 80 gigahertz, which is basically E-band here, right? So good technology from PA, LNA, and switch perspective. What about transceiver? So let's talk about the up-down conversion here, right? So the key component of up-down conversion is the phase noise, and as basically it berates, right, compared to in the frequency domain. So we have achieved around minus 106 dBc per hertz at a 1 megahertz offset. Very good tuning range you can achieve, 27%. There are different innovations have been done with our partners. Some of the things we are showing it here. The important thing to understand that there is another knob you can place by backgate bias. You can even improve the phase noise by 0.5 dB. That has been demonstrated by our partners from Brussels, right? So it's possible to do that. So that these are the kind of knobs we can tune in this platform to have a very good up-down converter. It's extremely important to understand because a lot of power is burned in the local oscillators alongside PA and ADC DAC. So we have to use a technology which is kind of not consuming too much power, at the same time give you very good performance in terms of phase noise. I will also show you this slide about the data converter. This is a single channel 18.5 gigasample per second 5-bit flash ADC. The point here is even at this sampling rate, the power consumption is less than 150 milliwatt. And that's the figure of merit, right, we use. Because as you go to higher sampling rate, that you have to do as you go to higher frequencies and higher bandwidth of your channels, you have to make sure how much power you're burning in your data converters. So this is a classic example of how FDX platform or FDSOI platform can be used for a low power dissipation of ADC-DC. Okay. This is the last example I will show, how this technology can be shown as a vehicle for even E-band, which is 71 to 86 gigahertz. This is a power amplifier at E-band demonstrated by one of our partners, which is KU Leuven. And they're showing around 18 dB gain, around 18 dB PSAT as well, and very good power efficiency at 76 gigahertz, right? Just to show that this technology can go up even beyond 50 gigahertz as well, and very good power density. That's also another important thing, right? Because people talk about going to 3.5 because of power density. So here in E-band, on a CMOS platform, we are showing 3 watt per millimeter square, which is not too bad. Not as good as, of course, silicon germanium or even 3.5 materials, but still good and one of the best in CMOS technology platform. Reliability, as I said, that these technologies have been qualified with our internal way of assessing the ruggedness and reliability, and it passed our test for ruggedness for 6:1 VSWR and at a 23 dBm of output power, right? And this is the way we basically characterize our technology. We basically make a PA which meeting the specs, run the waveform for 5G, and then test, right? And we do a lot of testing, and we cannot do, of course, for 10 years testing. What we accelerate the test, and then we have a very well calibrated model based on what we see the performance, we extrapolate to 10 years, right? And it shows that it can withstand 10 years of worst case reliability performance. And we have tested it for different degradation models, and it passed those tests. So this is basically available for product for millimeter wave and higher millimeter wave frequencies as well. So this is the slide I want to show the how it differentiates, right? It's a differentiated technology, how it differentiates from a bulk technology. So for an analog beamforming module, for a 8-element and antenna array, for a 7 dBm kind of a linear output power, the way we show that is that the PDC or the DC power dissipation is almost like 20% reduction at 20 nanometer bulk comparison, right? And that's the power of this differentiated platform. So we developed this platform particularly for high efficiency, high transmission power. And you can see that. If you go to digital beamforming, it will be even better because ADC, DAC power will be less, the LO generator power will be less. So that's the power of this technology. And the last two slides, I will show here that what our recommendation based on different partitioning of the millimeter wave radio. This is from UV perspective, user equipment perspective, like handset, tablets, laptops, even CPE, for example, right? So as you go from bulk CMOS to 22 FDX to 45 RFSOI, which is PDSOI, of course, the transmission powers will be better. You'll be more efficient transmission power there. From the transceiver perspective, I think FinFET is the best technology, but you can still integrate 22 FDX for transceiver with the FEM, right? You can do that. And that's where basically this is a very good platform from digital beamforming perspective. I'm not showing digital beamforming here, but it can be done from that perspective, right? So it depends on your power need or efficiency need. You can use any of this platform. Today, the technology that they are using today, based on Qualcomm's technology for millimeter wave handsets, are 20 nanometer technology. It's not efficient, but that's the only technology we are using it today. But in future, you will see that people will switch to other technologies. From the infrastructure perspective, small cells, micro cells, whatever you call it, the silicon germanium comes into picture. It can generate even higher power at a higher efficiency than 45 SOI. So that's also there. And you can see a lot of commercial products in the base stations for millimeter wave using silicon germanium today. But other technologies can be used as well. FinFET is still the best technology for transceiver purpose. 22 FDX can be a good technology for there as well. And of course, the baseband processing and everything is in the FinFET domain, right? So with that, I just want to just spend 1 minute here to introduce you the concept of differentiated foundry here. So you guys all know about TSMC and Samsung. Samsung is, of course, a vertically integrated. It's not a pure play foundry, but TSMC is. But they basically play with the Moore's law scaling, right? Which is basically going up to 5 nanometer today in commercial product, going to 3 nanometer and even beyond, right? And that's the way they play their game. Then there is the people who are the followers, we call it, right? They don't go to the bleeding edge as at the same time as these people. They're kind of 1 or 2 generations are kind of behind. And they normally don't go to the bleeding edge all the time, but they are the followers, right? So let's say there is a capacity issue, there is a second source issue. These are the people to take those volumes, right? That's the way they do. Whereas Global Foundry, we decided probably in, I think it's 2019, we have a decision at the corporate level that we don't go after this bleeding edge node beyond 12 nanometer. And why we did that, we did some calculations saying overall foundry market, which is around 63 billion, 75% of the market lies within 12 nanometer. Of course, there is a 25% market with a very high margin business also there. But we said that amount of investment we have to do, we rather put that investment for differentiation. And that's where differentiated foundry comes into picture. It is, you can see the effect of it in mobility, in IoT, in auto and photonics. And we spend more dollars in R&D there to differentiate ourselves compared to others in this domain. That's the reason it's a differentiated foundry, but not going to the Moore's law scale. Just want to make sure that people are on the same page, right? So that's all I have today. So as I talked about differentiated silicon technology, introduced the concept of silicon germanium, partially and fully depleted SOI for millimeter wave applications, covering KU, KA, and E band, and even beyond. And particularly for 22 FDX platform, very good SoC platform for millimeter wave, right? And it can be an ideal candidate for future digital beamforming as well. With that, I will finish today and take any questions that you may have.
Thank you, Dr. Bandipadhyay. So if anyone has any questions, please feel free to ask them either in the chat, or you can unmute yourself and ask your question as well.
I have a question about the RF backend.
Sure.
What are the limitations there? Yeah, just because I've worked with the, like I was saying before you started, worked with your 22 process and with the ST's 55 nanometer by CMOS, and the backends are a lot different. So
of course, yes. So let me understand your question. When you say what is the limitations, what do you mean by that? Are you thinking of where you can go, up to what frequency you can go? Is that what your question is?
Like, in my opinion, the ST process has a better backend, but I don't, and I imagine if you guys wanted to, you could make something equivalent, but I'm just trying to understand, you know, are there certain design choices that limit you from having certain thicknesses? Yeah.
Sure, that's a very good question. So just to give you some background here, right? So 22 FDX platform, when it was first developed, it was meant for digital SoC, right? And we thought at that point that it probably have another kind of a track than FinFET track. That was the whole idea. But we quickly realized that, you know, of course we have FinFET too. There's no point in having another parallel development in FDX. But the advantage that FDX brings in is RF analog mixed signal. So then we changed the concept to RF SoC. And this is still probably the best RF SoC technology today. So in order to do that, what we found out, in order for RF SoC technology, I'm not even talking about IoT, which is very, very cost sensitive market. Even for millimeter wave, when you go to a UE, like a handset, it's a very cost sensitive market, right? So here, of course, you have to basically bring the performance. Otherwise, it will be a performance and power at the same time, right? It's extremely important when you introduce a technology for a handset, it has to be power efficient because it will bleed all the power anyway, right? For millimeter wave, it's a very power hungry part of the electronics, right? So what we do is we basically make a kind of a compromise here. We think that, if we really want to go to raw performance, where it is less cost sensitive market, for example, just to give an example, infrastructure, right, is not as cost sensitive as consumer market like handset. So there you can basically, yes, you can develop a technology where you can have a leverage there by basically providing better performance. At the same time, your cost structure becomes slightly in the wrong way. In 22FDX, what we said that, okay, let's target the technology where you can place it alongside bulk technology. Of course, it is not as cheap as bulk, it can't be, but again, it provides a better performance and power that basically sell it, right? So that's the reason I don't think we optimize it to the extent that ST did for silicon germanium. But if you look into a silicon germanium offering, particularly the roadmap, there we have a lot of offerings for a better backend for a raw performance at higher frequencies. Does it answer your question?
Yeah, yes, it does. Thank you.
Any other question?
I have a question.
Sure.
So what is a roadmap for scaling this technology into smaller nodes?
That's a very good question, and I'm really glad you asked that question. Right, I didn't talk about in my presentation. So our plan is from 22 to go to 12 nanometer, and it's not because of digital scaling only, right? That's part of the reason. The other reason is, so for example, we have some roadmap of 22FDX platform itself, and we call it plus or plus plus, right? So 22FDX plus and plus plus. What it means is there is a generations of technology on 22FDX itself to improve the performance. So there is a roadmap for that as well. But at some point, we believe, particularly like application of digital beamforming, we have to have a technology going to the next node. At the same time, not compromising the RF performance, right? So here it's very important to understand that a lot of people think, well, FinFET can do everything. Well, FinFET can't. If it is so, then there will be a Moore's law scaling for RF millimeter wave in FinFET as well. It's very easy, actually, right? Up to transceiver, that is to some extent true. Not totally, but to some extent true. But when you go to front end, it's not true anymore, right? So we have to make sure when we migrate the technology from 22 to 12 nanometer, we of course bring the advantage of power performance scaling, but at the same time, not to lose out on the RF millimeter wave performance. And that's basically what we are planning right now. So answering your question, the next node of 22 FDX will be 12 nanometer, and we call it 12 FDX. So it will address markets like digital beamforming, because digital beamforming market is still not here, right? There are some examples of it. It's mostly used in sub-6 gigahertz massive MIMO, to be frank with you. For millimeter wave, it's not there yet, but it will come in, and we know that. Particularly by thinking about 6G, for example, right? There will be a lot of digital beamforming. So we are planning for a 12 nanometer shrink to this technology for that purpose. At the same time, maintaining the millimeter wave performance roadmap to a higher performance for that purpose.
Thank you.
Any other question? So I have a question for you, just to understand that, I'm assuming that a lot of people here, they're faculty members and research students as well. So what's your focus or interest in this domain? Are you guys looking into millimeter wave broadband application like mobility or satellite communications, or all of them, or sensing? I just want to know, that's all.
So our group, which there's more members now here, we do sensing, like we have like 80, 160, I think, gigahertz.
How much gigahertz?
160.
Oh, 160 gigahertz. Oh, okay, good. Yeah.
Right. I think that's right. Because I didn't work on that. Like distance sensors for ADAS stuff, I think.
So then probably it will be 140 gigahertz, isn't it? Because that's where a lot of our clients are working, and they're asking us for information about future technology. So
Yeah.
120 and 140, but maybe the people are working even beyond that. So you guys are researchers, right? You always lead us. So yeah.
I'm
Okay.
pretty sure it's 160.
Okay.
And then we do some mixed signal stuff too.
When you say mixed signal, are you talking about an SOC or just analog mixed signal in sub-6 gigahertz and other applications?
Like a high bandwidth ADC lane. And
oh, okay. Okay. I see. Okay.
That's what Eric did. Eric's here.
Okay.
Yeah.
You guys hear me?
And for ADC, DAC, which technology platform you use for your research?
Sorry, who are you talking to?
No, I'm just asking, when you say ADC, so ADC, DAC, what technology platform you use for your research?
Oh, all this stuff I just listed is what we do in 22 FDSOI.
Oh, 22 FDSOI. Okay.
Yeah, yeah. We do stuff. We do 22 FDSOI and we do the STs by CMOS 55.
Okay.
Yeah.
And the reason you use 55 STs technology, is it because it also has a lot of high density logic gates? Is that the reason why you choose 55 nanometer?
Oh, that's for the HPTs, for the high FTF max, for like high bandwidth.
Okay, I see. So the way we look at it is this. Of course, you can take advantage of the advanced lithography to reduce the parasitics, but to a fast order, you don't gain too much in terms of your HBT performance by going to a lower node. A lot of people who work with us, and we have a lot of clients in different applications also, the reason we are going to lower nodes for SIGI is that we wanted to have an advanced or higher density of logic and memory into the platform. That's the reason. Of course, it improves. I totally agree with you that we also see that we have a 90 nanometer SIGI technology, and we have a Fmax much better than our 130 nanometer, and that's partly because we optimize the technology for a better performance, and partly because we get the advantage of the advanced lithography for your parasitics.
Mm-hmm. Yeah, our group doesn't really integrate any sort of digital stuff.
Okay, you don't. Okay.
At all.
Okay.
At all, yeah.
I remember a long time back, I met Soren in one of the, it's an IMS conference, and he was telling that at that point, probably it's almost like I was in IBM at that point, he was saying people should jump from a conventional 24, 28. At that point, nobody was talking about 37, 39 even. He was saying we should talk about 120, 140, 160 gigahertz at that point. And he was telling sensing to start with. Backhaul is another application, which is absolutely right. And this is going right. So today backhaul is going to W band, and the next journey will be D band. So he was spot on at that point. So I still remember that conversation I had with him.
Sorry, this is a conversation you had with who?
Professor Sorin Vanigescu.
Oh, okay. Yeah. Well, that's what's going on.
Yeah, no, I totally agree. And he was basically talking about that 5 years back. So
yeah.
Okay, any more questions? Okay, if no more question, thank you for joining. And again, you have my email address. Any question you have, we are always looking forward to collaboration with academics, and we have a very good university programs. That's the reason I know Sorin very well, right? So please feel free to shoot me email, and we'll go from there. Thank you.
Thank you.
Thank you.